So we are, as we mentioned also last time in this set of lectures, we are going really under the hood of GIS applications, trying to understand what is really inside all these programs that work with GIS. How do we do certain things in GIS software? What data formats we use? And last time in this introductory lecture, we looked at two big questions in GIS. One is the location question, understanding where the two segments intersect, or whether a certain point P is to the left or right of a segment AB. And we will need a lot of linear algebra. Well, not a lot of, but some linear algebra on that. And this is what we will be doing today. I will give like a quick introduction to the necessary linear algebra. And the other question that we looked at is, yes, understanding who is the closest to which site, and using particular Voronoi diagrams for that. So that's what we were doing last time, and this part is essentially done. We no longer returning to the Voronoi diagram and going into other questions today. So now we are doing this linear algebra, but in particular with applications to point location. And of course, linear algebra is, looks like I stopped sharing my screen. Is that true? I'll restart screen sharing. Okay. Yes, hopefully it's there now. So I'm on, well, slide 4 in our set of slides. So hopefully you're able to follow also with that. So before we go to the linear algebra, which is one of the most basic math subjects, let's look at the most basic and most important notions in all of mathematics. What are they? Well, those of you who have taken other courses with me, you might have seen my definition of the most important and most basic notion in math. That's the notion of a set. It's not definable, that's why it's so basic. So we're saying that a set, is just a collection, a bunch, a set of things, elements of the set. What's important is understanding which elements belong to the set and which elements do not. And given two sets, x and y, we can form the set of all possible pairs, where small x is in the set large X and small y is in the set large Y. And that set, the set of all pairs, is called the Cartesian product. And in particular, the notion of the function, which is another very important fundamental notion in the math, is, well, it's a mapping from X to Y. It can be understood as a subset of the Cartesian product, X times Y. So here we have the Cartesian product, and here is this curve, which shows you the graph of the function. You can think of the graph of the function as of a subset of the Cartesian product of X and Y. For a second. So yes, we were talking about the Cartesian product of two sets. One of the most important Cartesian products that you may encounter in mathematics is the Euclidean plane, the R squared, or sometimes we will call it just R2. So yes, that's a product of real line times the real line, or in the other words, it's the set of two-dimensional vectors like this. Okay, so set of pairs of numbers or points in the plane. You can also use polar coordinates. You can also say that they're complex numbers. So there are lots and lots of ways in which the same object, the R2, under which the same object is known. So anyway, the product of the real line and itself, the set of pairs of numbers, of vectors, and so on. That's the R2, or R squared, with which we will be working. And similarly, you can define Rn. It's an n-fold product of a real line, set of all n tuples of real numbers, so vectors of length n, and so on. So a few conventions or notations that we will be using in this course. So any point in the two-dimensional plane has two coordinates, or any vector has two components, px and py. Sometimes we will be denoting them as p1 and p2, or using this MATLAB style, p1 and p2. So if p is a vector or a matrix with two entries, then the first entry is denoted as p of 1, the second entry is denoted p of 2. So that's very much like MATLAB style. It's pretty convenient, and then if you ever need to implement things in MATLAB, then it's kind of directly, you can take it from the lectures. So by default, the vectors will be column vectors. So the vectors can be row vectors like 1, 2, or they can be column vectors like 1, 2. And by default, a vector is a column vector like this. So to go between the column vectors and row vectors, we use the transposition. So if you have a row vector and apply the transposition operator to it, it becomes a column vector. So you have vector like this, 1, 2. At this point, I might have wanted to start using Jamboard, but I'll skip it. So if you transpose this, then the vector becomes a column vector, and vice versa. So if you do the transposition of a column vector, you get a row vector. And again, using MATLAB notation, we will use just the apostrophe to denote the transposition. That's how MATLAB denotes transposition. Now again, with the conventions as in MATLAB, if you want to list the elements of a row vector, you can just use spaces between the elements. So you can use commas, or commas and spaces, that doesn't matter. So all these things mean the same thing, the row vector 1, 2. The semicolon is in MATLAB denotes the new row. In particular, if you have a column vector like this, so 1, 2 is a row vector, you have the transposition, so this is really a column vector. Another way to specify the column vector is specify it like this: 1 semicolon 2. So it's like 1, and then you start new row because of the semicolon, and then you have 2. So this is another way to specify the column vector. Again, this is pretty standard in MATLAB. You can get used to it also during this course. And while the transposition is its own inverse, so the transpose of the transpose is the original vector, right? So if you have this column vector and apply the transposition to it, then you get a row vector like that. Let's just play with changing columns and rows back and forth. Standard thing in linear algebra and also in MATLAB, and well, we will be using this notation. Okay, some properties of the Euclidean plane of R square or R2. It's a vector space, so you can add its elements and you can multiply them by numbers. So if you have two vectors P and Q, then the sum of them is taken component-wise. The first component of the sum is the sum of the first components. The second component of the sum is the sum of the second components. And you can multiply vectors by a number. Again, you do the multiplication component-wise. It's easier to see than me trying to read what this really means. So the dimension of R2 is 2. The maximum number of linearly independent vectors is 2. In particular, here are the two linearly independent vectors, which are called the standard basis for R2. Any two linearly independent vectors form a basis, but these are called the standard basic vectors, or standard basis 1, 0, and 0, 1. And any vector can be written as the sum of its first coordinate times E1 times this vector plus its second coordinate times E2 times the second vector. And I'll try again to scribble here something with my mouse, but maybe I will go to Jamboard sooner. So yes, if you have a vector of, I don't know, like 3, 2, then the first coordinate of the vector is 3, and you can multiply it by the first basic vector, 0, 1, and add to it the second component of the vector and multiply it by the second basic vector. And well, 3 times 1 is 3, 3 times 0 is 0, and 2 times 0 is 0, 2 times 1 is 2, So you can verify that this holds, well, in this example, but also it holds in general. So the R2 can be turned into an Euclidean space. Euclidean space is a space with a scalar product. So you can define the scalar product of two vectors as the product of the first two components plus the product of the second two components. And this is the same as the absolute value of the first vector times the absolute value of the second vector times the cosine of the angle between them. So, well, let me still continue here. If you have two vectors like 3, 2, and I don't know, maybe 1, 2, then the scalar product of these two, if you multiply one by another, what you do, well, you multiply in the first components and you multiply in the second components, and then you sum those two things. That's your answer. That's the scalar product. Scalar product is a number, and this is how it's obtained. Okay, and we will be denoting scalar product, well, maybe like this. You can see the notation like this, maybe like this, just by having the multiplication sign between the two vectors, or just omitting any multiplication sign, just like that. And similar, you can define the scalar product for vectors of high dimensions, 3 and n. Again, you multiply the corresponding components and you take the sum of what you have obtained. Okay, so that's the scalar product. Again, I'm hoping that you're not seeing it for the first time, but if you do, well, that's what it is. Next thing is matrices. So vectors are kind of rows or columns of numbers. And well, matrices are the whole tables of numbers with multiple rows and multiple columns. So here is an example. It has 3 rows, 3 columns, and the element in row I and column J will be denoted like this, Aij, or often using, again, MATLAB style, we will be referring to it like this, A of Ij. So again, here is the matrix. And the matrix has 3 rows. So we can write this matrix in a single line by just listing the 3 rows and separating them with the semicolons. Remember, the semicolon is the sign for new line. So it's this row, then new line, this row, new line, this row. So these are really the same things. This is just, I don't know if it's easier. It's a single row, but I think this one here on the left is kind of, it's more easy to see what this matrix is. So yes, it has 3 rows, 3 columns. And if you take the element in the second row and the third column, A to 3, well, that element is 6. Here we go. So matrices of same size, if you take 3 by 3 or 2 by 2 matrices, they also form a vector space. You can add 2 matrices, add them component wise. You can multiply them by numbers, again, element by element. Vectors are special cases of the matrices. So a column vector is a matrix with with m rows and 1 column, and similarly a row matrix is a matrix with, well, 1 row and some number of columns, n. So both of these are matrices. So we're talking about the transposition operation of transforming row vectors into column vectors. That generalizes to transposing matrices. Again, if you take a matrix and you take its transpose, then you turn the rows of the matrix into columns. So if we take, again, this matrix A, 1, 2, 3, 4, 5, 6, and so on, and take its transpose, then we will get the matrix in which the rows of A become the columns of A transpose. So the first row of A is 1, 2, 3. That becomes the first column of A transpose. The second row of A is 4, 5, 6. That becomes the second column of A transpose. And the third row of A becomes the third row of A transpose. Again, I apologize for my scribbling, but hopefully you understand what it is. For something more important, I'll go to Jamboard. So here is A transpose. The first row is 1, 4, 7, followed by row 2, 5, 8, followed by row 3, 6, 9. Okay, so when you transpose the rows and columns, you change rows to columns, columns to rows. Now in MATLAB, there is a neat way to refer to the certain row or column of a matrix. So notation like this means the ith row of the matrix. So, okay, I have an example down below, so I'm not going to draw it. So for instance, over here, this notation means the second row of A. This notation. This means the first row of A. Well, here it is, 1, 2, 3. And similarly, notation like this, column, comma, number, like this. This means the second column of A. And the second column of A is 2, 5, 8. It's a column vector. So here it is, 2, 5, 8 transpose. Okay. And in general, if B is equal to A transpose, then the ith column of B is equal to ith row of A. Okay, so again, maybe if you see it for the first time, it may seem like quite a lot of material, but hopefully you've seen it. If not, you can play with it in MATLAB and learn elsewhere. Okay, I guess last but not least thing, matrix multiplication. If you have two matrices and the number of rows in one of them is equal to the number of columns in the other, so the dimensions have to match. Well, the number of columns in A should be equal to the number of rows in B. Then you can form the product of the two matrices, A and B, and the element ij in the product is equal to the product of ith row of A and jth column of B. And this product is really the scalar product. So again, if you have A and you multiply it by B, then when you take the ith row of A and jth column of B, so the scalar product of these two things, note that they will have the same number of elements. The number of columns in A is equal to the number of rows in B. Both of them are P. So these are vectors of the same length, or vectors with the same number of elements. You can form the scalar product, and that scalar product will be the entry ij in the matrix C, where C is the product of A and B. Okay, that's matrix multiplication. Diagonal matrix. So a matrix which has zeros everywhere except the diagonal. So 0 and 0. It's denoted like this, diag of A, B. The first element in the first row is A, the second element in the second row is B, everything else are zeros. Identity matrix is the matrix that has ones on the diagonal, like this. 1, 0, 0, 1. That's the identity matrix. It's called the identity matrix because you can multiply any matrix by the identity matrix from one or the other side, and the matrix will not change. So it's like 1 in numbers. And moreover, it has a square matrix, and you can find a matrix such that when you multiply this matrix by A, you get the identity matrix. Then B is called the inverse of A, and A is invertible. Okay, so it's like 1 divided by A. So that's the inverse of a matrix. The inverse of a matrix is a matrix such that when you multiply the matrix by it, you get the identity matrix. Okay, so A inverse times A is equal to the identity matrix. Okay, some properties of matrix multiplication. So if you take a matrix and multiply it by a vector, it's like multiplying the first column of the matrix by the first element of the vector and multiplying the second column of the matrix by the second element of the vector and taking the sum. So let me have an example. Try to clear things now. I guess I'll go now to Jamboard because there is quite a lot of things that I would need to. It's a third page. Okay, So we are now looking at this property of matrix multiplication, that if you multiply a matrix by a vector, then it's the same as multiplying the first column of the matrix by the first element of the vector plus the second column of the matrix times the second element of the vector. And we are talking about 2 by 2 matrices now, so we only have this, 2 columns, and in the vectors we have 2 elements. So for an example, I don't know, let's take an arbitrary matrix 1, 2, 3, 4 and multiply it by another vector, by a vector or by another matrix 5, 6. So what will be the answer? Well, what do we have here as the first element in this matrix? We have the product of this row and this column. So it's 1 times 5 plus 2 times 6. What do we have over here? We have the product of this row and again this column. Remember, when C is equal to the product of 2 matrices, then Cij is the product of ith row of A and jth column of B. Okay, so for instance, over here is the element in the second row and first column of this vector, and it's obtained by taking the second row of this matrix and first and only column of this matrix and taking their product, scalar product, which is 3 times 5 plus 4 times 6. Okay, whatever those are, so this is 5 plus 12, this is 17, and this is 15 plus 24, 39, hopefully correct. Anyway, that's the that's doing this product by definition. So if you do by definition, this is what we obtain. And now let's do the same product, but using this property. Okay, and the claim is that the result should be the product of the first entry of the vector times the first column of A. First column of A, here it is, plus the second entry of the vector, or the second coordinate of the vector, times the second column of A. Here is the second column, 2, 4. And if we do that, well, 5 times 1, 3 is 5, 15. 6 times 2, 4 is 12, 24. And I guess when you sum these up, you should get the same answer. 5 plus 12 is 17. 15 plus 24 is 39. And not only that there is any magic that you got the same numbers, but also you can see that you're really doing the same things. So in order to obtain this entry, you multiply this vector by this row. Well, how do you do that? You multiply the first element of this vector by the elements of this row. And this is what you do both here and here. You take the sum of what you got. So it's the same thing. So in general, the matrix multiplication acts column-wise on the second matrix and row-wise on the first matrix. So, well, if you really need a shorthand for that, if you have a matrix A and you multiply it by a concatenation of matrices B and C, then it's the same as multiplying A by B and then multiplying A by C and concatenating the two products. And similarly, if you have matrix A and below it you have matrix B, see there are semicolons, so meaning you put in them one on top of the other, and multiplying it by a common matrix C, then it's like you multiplying A by C. So if you have two matrices one on top of another and you're multiplying them by C, then you can multiply the first matrix by C, then the second matrix by C, and put one product on top of the other. So that's matrix multiplication. There are also some properties of matrix addition. A plus B is equal to B plus A, although the product in general is not commutative. You have the distribution law, just like with numbers. You have the associative law, just as with numbers. So it's interesting that if you multiply two matrices and they take the transpose, it's like taking the transposes and multiplying them. I think it should be in the opposite direction. I might have made a mistake here. It should be B prime times A prime. I'll correct that. We will not check that, but I'll make the correction. And the inverse of A, if you transpose that, is the same as taking the inverse of the transpose of the matrix. Okay, so again, we will not verify these properties, but well, here are all the properties that you need to know. Well, maybe even more that you need to know for this course, but in general, it's good to know them. Okay, so let's continue. Those were the basic things or some of the properties of matrix multiplication. Determinant. You can define something called the determinant for a 2x2 matrix A, B, C, D. The determinant is, well, this number. So how does it look like? It's probably easier to see when you have the matrix in the stable form. So I'll go to the next page in the Jamboard to write the determinant of the matrix. So the determinant of the matrix A, B, C, D is this number AD minus BC. So you take the product of these entries and you subtract the product of these entries. So I go like crisscross. So for a 2x2 matrix, this is what the determinant is. And geometrically, what determinant means is the area of the parallelogram built on the vectors. So if you have the vector AB over here, the red vector, and you have the vector CD over here, the blue vector, then the determinant is equal to the area of this parallelogram. So you take the sum of the vectors, or you put the two vectors like this, and you can see that the area of this parallelogram is exactly equal to AD minus BC. So again, let's see why it is so. So you have the vectors. So this vector is AB, and this other vector is C. This is CD. Then you can take the area of this full rectangle, which is A plus C times B plus D, and subtract the areas of this triangle, and this rectangle, and do it twice because you do it here and also do it on top. And you'll see that this will be exactly equal to the area of the parallelogram, area of this parallelogram. Now, if you have the situation like this, when in order to go from the vector AB to the vector CD, you have to rotate clockwise, then again, the determinant will be equal to the area of the parallelogram, but with the negative sign. So the determinant is really the signed area of this parallelogram built in vectors A, B, and CD. And the reason why this is important, now we're finally coming to applications in GIS, it lets you determine whether a point is on one or another side of a line. So remember our question where, one of the GIS questions from map overlay, we wanted to understand whether two segments, PQ and AB, intersect. And one thing we would need to know for that is whether the point P lies to the left or to the right of the line from A to B. And how can you determine that? Well, you can form something that's called vector product. In general, it is defined for vectors in 3 dimensions, but for vectors in 2D, we can say that the vector product of two vectors is just the determinant like this. And we know that the determinant is positive or negative. So from here, we know that the determinant is the signed area of this parallelogram. And in particular, if you look at the sign of the determinant, whether it is positive or negative, you can determine whether you have to rotate to the left or to the right when you go from the first vector to the second vector. So over here on the left, you're rotating counterclockwise from red to blue vector. Here you're rotating clockwise from red to blue. And depending on that, the determinant, or equivalently the vector product, will have either positive or negative sign, because it will be plus the area of the parallelogram or minus the area of the parallelogram. And in particular, coming back to the question of segment intersection, in order to understand whether a point P lies left or right of the line AB, you form two vectors. One of them is the vector AB, and the other one going from A to P. And you take the determinant of these two vectors, or the vector product of these two vectors, this vector AP and vector AB. And if you have to rotate clockwise from this vector to the vector AB, then the determinant will be negative. And if you rotate counterclockwise, like here from AQ to AB, then the determinant will be positive. Okay, like this. That meant not to be minus, that meant to be underscoring. And understanding whether different, on which sides of one segment the endpoints of the other segment lies, you can get whether the two segments intersect using the vector product, and the vector product you can do using the determinant. Okay, so long story with the determinants, matrices and other things, and short answer to the question of whether one point lies, whether a point lies on the left or the right of a line. Okay, so that was the answer to one of the questions. Another reason why you may want to use the vector product and the determinants is to determine the areas of polygons. So again, it's quite a natural GIS question. You are given a polygon like this. So here is the polygon, this whole line. The black line defines the polygon, and you want to know the area of the polygon. How do you calculate the area of the polygon? Well, there are many ways to do it, but one of the simplest ways is to choose the origin arbitrarily. So take some point O as your origin, and then go through the edges of the polygon one by one. So here is one of the edges, here is another edge, here is another edge, and so on. Well, here is yet another edge. So you go through all the edges. And when you go from the ith vertex of the polygon to vertex I plus 1, then it may happen that you rotate the vector from the origin clockwise, right? To get from this vector to this vector, you have to rotate clockwise. Or it could be that in order to get from this vector to this vector, you have to rotate counterclockwise, right? And you can observe that the area of the polygon is equal to the total area of triangles like this, like the red one, when you have to rotate clockwise to go from one point to the next. So this is one triangle. Well, here would be another triangle like this. So if you look at this edge. So all these triangles, well, you can take the sum of their areas, and they will give you the polygon area, but they will also calculate extra area like this. And you don't want to have this area in your polygon because it's outside of the polygon. So what you would have to do, you would have to subtract from all the area of red triangles, the areas of blue triangles like this. So this should be subtracted. The area of this triangle should be subtracted, and so on. And the nice thing is that the red triangles differ from blue triangles exactly in the way in which the vector from O rotates, right? As we started from observing here, from OVI to OVI plus 1, you rotate clockwise. Here from OVI to OVI plus 1, you rotate counterclockwise. So if you take the vector product of these two vectors, then you will be adding the areas of triangles like this, and you will be subtracting the areas of the triangles like this, exactly as you need for the computation of the area of the polygon. Right, so going back to the previous slide with the parallelograms, or with vector products. So the vector product is, remember, positive or negative, depending on whether you rotate clockwise or counterclockwise from one vector to the other. And that's exactly what you are using in here in calculating the areas. You're adding these areas and you're subtracting these areas. And both addition and subtraction can be written just as the vector product, just as the determinant. And you have a 1/2 over here because really the determinant, as we know, is the area of the parallelogram, which would be built on these vectors. If I move this vector over here, and if I move this vector over here, but the area of the triangle is 1/2 of the area of the parallelogram. So that's why you're multiplying it by 1/2. So this vector product gives you a really simple way. Vector product and determinants give you a simple way to calculate the area of an arbitrary polygon. You don't have to triangulate the polygon. I mean, there are other ways to calculate the area. You can, split it into triangles and then calculate the area of every triangle separately. But triangulation is, well, quite complicated, and then you would have to calculate all the areas of the triangles. Instead, you just choose the origin arbitrarily. It doesn't matter where this point is, inside polygon or outside polygon, and just do this simple summation for all the edges of the polygon. You calculate in this simple vector product, which is the same as calculating a determinant. And adding up, you get the area of the polygon. So speaking of the ways to represent data in GIS, yes, the data can be represented like this, kind of in a continuous manner. The vertices of this polygon can be anywhere. An alternative way, an alternative data format for GIS is having the vertices of polygons and everything else on the grid. So you have a grid, and the vertices of the polygon must stay on the grid. And it's interesting that if you have such a polygon whose vertices are on the grid, then you can calculate this area differently. You can its area differently. You can calculate the number of points inside the polygon plus 1/2 of the number of points on the boundary of the polygon, subtract 1, and that will give you the area of the polygon. So this is known as Pick's formula. We're not going to prove it, but just for information, that's how you can calculate the area of a polygon with vertices on the grid. Okay, so let's see, we have 3 minutes remaining. Let me just finish, I guess, this hour by, again, repeating that, well, by this time repeating, but also stating it more clearly, that in GIS, there are 2 types of the data, or there are 2 ways in which the data may be represented. One is the so-called vector format, and the other is so-called raster format or grid format. So the data types could be a point. So a point could have coordinates, and these coordinates can be arbitrary numbers, x and y, and yes, they are just numbers in R2. Well, each of them is a number. You can have lines, again, with vertices at arbitrary points. You can have polygons with vertices in arbitrary points, and so on. So in particular, with this data format, you can represent not only 2-dimensional objects, but also 3-dimensional objects by meshes or terrains. And one way to represent terrain is, I'm now starting to draw in the Jamboard, is to take your region of interest, which may be this square, take some triangulation of it, trying to draw triangles that split this region of interest, or the partition, the region of interest. And then for every vertex in this triangulation to specify the height of the terrain. And you will get something which, well, may look like this. So you know the heights at all these points, and then you just do the linear interpolation between the points. And that's a very precise way to specify the data. It's kind of compact, but it's pretty hard to do computations with this data. And an alternative way to represent data is this raster data. For terrains, this is something called the digital elevation map. While it may be more relevant for, for urban environments, where you really have sharp edges and steep slopes. Digital elevation map just takes a grid and specifies the elevation of the terrain at every grid point. So there is no interpolation. Like here, you don't need these triangles. Just have the height of the terrain at every point. Okay, so those are the examples of GIS data type, I guess. Or rather, resume recording. So yes, we have two different types, data types, in particular in GIS, the vector with full precision and raster when you're confined to the grid. And of course, one important question is how do you go between the two kinds of data types? So if you have a vector data, like over here, you have this red, I don't know, whatever it is, a road, a river, and you want to represent this red polyline with, with some pixels, with some pixelated data to convert it to raster. Well, you can just look at the pixels through which this line goes. It goes through this pixel, this, and so on, and hit those pixels. So you will say, well, my line is represented by these blue pixels over here. And of course, that's not necessarily a very good representation because, well, this red thing is a linear feature. It's a road or a river. And yeah, these blue pixels that represent this red line in the raster format, well, they are not even forming a line, or the centers are not forming a line. So you do have some loss of precision. And then there is also a question between, well, whether you represent it really by the pixels or by the centers of the pixels. So maybe only the centers of these pixels represent your line. There's also a difference between snapping only the endpoints of the line versus well, snapping the whole segment or the whole road. In particular here, now I'll try to change the color of anyway, so that's how you can change the vector data to raster data by just looking at the pixels through which the line goes. And on the next slide, we will have a specific example of how it can be done. So changing the raster format to vector is a more complicated thing. So, well, you can have, like here on the picture, all these blue pixels that represent, well, your red segment. And the question is really, how do you fit the best red segment into these blue pixels? Do you fit one segment or do you fit several segments? And if you fit several segments, which segments will you fit into which subsets of the data? Maybe you will fit one segment into this part, another segment into this part, and then, well, maybe these parts should be overlapping. So there is no unique answer of how you would represent different sets of pixels with lines. But if you do know which pixels you want to represent with a line, then you can do least square fit or things like that. And we will look at examples at the next slide. Of course, what happens is that, well, when you are going from the pixel representation to the vector representation, you may also lose precision because, well, the pixels, you know where they are, and who knows how your red line, how the vector data that you represent your pixel data with, how it goes. I mean, it really depends on how you fit, where you fit, what you fit in, and so on. So the question of conversion between the two data formats is far from being solved, or at least not necessarily solved uniquely. But nevertheless, we will look into a couple of ways of going between the vector and raster data, back and forth. So first example here on the left is the so-called Bresenham algorithm. This is the algorithm for going from the vector data to the raster data to the pixels. It works segment by segment. So you take this red segment, which right now represents the some data in the vector format, and try to represent this red segment with a sequence of pixels. So the Bresenham algorithm is a pretty simple algorithm. It looks at the pixels through which the red line passes, and it actually works slightly differently depending on what slope the red line has, whether it goes like this, like this, like this, or like this. It's a directed line. And we will only look at this particular case when it has small slope, slope less than 1, and the line is in the first quadrant. So it's in this north, whatever, east to west, northeast quadrant. So if the line goes like this, like we have here at the bottom, okay, it goes through the grid. So which pixels would represent the line in the grid? Well, the starting pixel is what it is, and the ending pixel is what it is. It's where the segment starts and ends. And then every time when you go to the right, you look at the pixel centers, one above and one at the same height as the previous point was, and you look at this point on the line and checking whether it is closer to this pixel center or to this pixel center. So a very simple algorithm. You kind of look at the middle of the pixels. You see where this middle intersects the segment, the given line, the red thing, and you either hit this pixel or this pixel, depending on which is closer. And in our case, of course, this pixel center is closer. So you're saying that, well, this will be the next pixel that represents this line. This is the first, this is the next, and so on. So you continue, you move to the next vertical line. You look at the two pixel centers, this one and this one. This is closer. So here is the pixel, the next pixel that represents this line. And you continue. Here again, you move. Well, I don't know how precise I was here, but assume that this thing is closer than that. So this pixel is hit. Then again, you move to the next half pixel, and you see that now, well, this point is closer to this pixel center, so you're hitting up this pixel, and so on, and so on and so forth. So this is the Bresenham algorithm. Pretty simple, converts a linear feature into a set of pixels. That's pretty standard. There is a procedure, Bresenham, in MATLAB, I guess, and probably in other languages too. So one simple way to convert raster data to, vector data to raster data. Simple, because in general, conversion of vectors to raster data is, well, conceptually simple. Now, the conversion in the other way, we are given all these blue pixels, and let's say we want to represent them with a single line. And what would be the best line? Well, one possible way to find the best line, or to define the best line, is to do the regression. So, you know, you look at the pixel centers. That gives you a set of points. I'll just put some points here in the, well, those were supposed to be points, whatever. You have some data, you have some points, and you want to find the line that goes through these points, minimizing some kind of the error. And one common error to minimize is the so-called sum of squared errors. I guess you have seen things like this. It's called the regression. So at every point, you look at the distance between the point and the line, well, the vertical distance between the point and the line, and you take in the squares of those things, and you're trying to minimize the sum of squares. So sum of squared deviations. Okay, and I hope you've seen how to do regression. If not, well, here it is. So if your line is given by the equation y is equal ax plus b, then here is the sum of squared errors. You take the derivative with respect to b, well, set it to 0, and this is your b. You take the derivative with respect to a, set it to 0, and this gives you a. So you substitute a from here. Sorry, you substitute b from here to here. You get an equation in a only. Here is the solution of the equation. And well, then you substitute the obtained value of a into here. And here is your answer for b. I hope you have seen these formulas when you were doing regression. If not, well, here they are. One particular simple way to do the regression and to understand what the coefficients a and b are in the optimal regression line is to move the origin to the center of mass. So assume that the average y and average x are equal to 0, and then these formulas simplify a lot because these become equal to 0. And in particular, then you're looking at the line going through the origin. So your b is equal to 0, and you only have a simple formula for a. But anyway, I won't go into the details because I hope that you have seen it in statistics or linear algebra course. If not, well, I'm not really teaching linear regression in GIS course. And here is something new that you might not have seen, and something that I do want to stop for some time, and we'll probably go to the Jamboard soon, is trying to find the line again that fits through a given set of points, but not really doing the regression. Instead, trying to minimize the square distance from the line to the given points.
Okay, so first of all, what is the difference between the regression and finding the line to minimize the sum of square distances? In the regression case, you assume that there is, some kind of coordinate axis, x and y, and you have your data points, the blue things, and you want to draw the line, and you assume that this line represents some kind of functional dependence. Y is a function of x. And when you're measuring the error of how well your line approximates your points, you're measuring this vertical distance, and you're summing these vertical distances to the line to and trying to find the line that minimizes the sum of those vertical distances squared. In case of GIS, your points just represent some data that are not necessarily connected to any kind of coordinate axis, and the coordinate axis, even if they do exist, well, they may be oriented like this. So in this case, well, your distance from your points to your lines would be like, well, infinite. So I drew this y almost parallel to the red line. So in GIS, we actually don't assume that there are any kind of coordinate axis. We just have points, and we want to find a line that minimizes the sum of square distances from the line to the point. So this is one of such distances. This is another such distance. We don't measure it vertically or in any other direction, well, because there is no notion of being vertical or having any other direction. Okay, so that's the line that we want to find, the line that minimizes the sum of such square distances to it from the given points. And the first question to ask is, what is the equation of a line? So we want to find a line. How do we represent lines? And there are various ways how you can represent lines. maybe the easiest one is to say that, well, you have some point x0, y0 that belongs to a line, and the line runs in a certain direction, and you take the unit normal vector to that direction. So some vector with coordinates cosine phi and sine phi for some angle phi. And then for any point x, y on the line, what you have is that this vector is perpendicular to this vector, to the normal of the line. And how do you write that two vectors are perpendicular? Well, what is this vector? It is x minus x0 and y minus y0. And this vector is cosine phi and sine phi. So you do the scalar product of the two vectors, and you want them, the vectors, to be perpendicular, so you want the scalar product to be equal to 0. Okay, again, hopefully this is something that you've seen before, but if not, well, this is how it's done. So, we can rewrite this equation as x cosine phi plus y sine phi. Here is x cosine phi, y sine phi, and well, the rest here is constant. X0 is constant, y0 is constant. So we say plus some constant is equal to 0. So that's the equation of a line. Okay. So now we want to find a line like this, which minimizes the distance, the square distance to our blue points. Now, what is the distance from a point to a line? Well, you can have a point, I don't know, AB, and you're trying to find this distance D from the point to the line. Okay. So what would be the coordinate of this point if the coordinate of this point is AB? Well, this vector from AB to the line goes in the direction minus cosine phi sine phi, right? So this vector normal to the line was cosine phi and sine phi. So this vector goes in the opposite direction, and hence this point will have coordinates, put it here, a minus d cosine phi, and y, sorry, and b, the y coordinate will be b minus d sine phi. Okay, so these will be the coordinates of this point. Now we know this point belongs to the line, so so that's the coordinates of the point. Any point that belongs to the line has to satisfy this equation, where x and y are the coordinates of the point. So the coordinates of this point should satisfy this equation. This times cosine phi plus this times sine phi plus d should equal to 0. Okay, and if you open the parentheses, well, you have, so this times cosine phi is a times cosine phi minus d cosine squared phi. Now here, b times sine phi minus d times sine squared phi plus d is equal to 0. And of course, cosine squared plus sine squared is equal to 1. So you know that the distance from point AB to this line, to a line given with this equation, d is equal to a cosine phi plus, sorry, plus y coordinate, which is b sine phi plus d. Okay, and of course this is for the point AB, which lies on this side of the line, in the same direction where the normal vector to the line goes. If your point lies in this direction from the line, then d is equal to minus this, or in general, d is equal to the absolute value of this expression. Okay, so that's the distance from a point to a line, if you haven't seen that. Now I'm returning back to the slides, and here I'm writing the sum that we want to minimize. We want to minimize the sum of squared distances from the points. So xi and yi are our blue points that are given to us. And the distance from any such point to a line is given by this expression, as we just derived. And we taken the square of it. And we taken the sum over all points. Okay, and now when we open this up, well, cosine squared goes out and you have these, sine squared goes out and you have these, then n times you have the d squared, and then you have the cross products, 2 times sine phi cosine phi, which is sine of 2 phi, the cross products of these, and then you have these cross products and these cross products. So this is the expression that we want to minimize. And one thing that we may want to do, just as we had with the regression line, is we may say that, well, the centroid of the blue points is at the origin. And hence, the line goes through the origin. D is equal to 0. So these are equal to 0. These are equal to 0. The line that goes through 0 has D equals 0, because of course, if you go back to to Jamboard, the equation of the line going through the origin, well, has to have D equal 0. Okay, so then you, in this summation, in this formula for our objective function that we want to minimize, we take, well, there are not too many terms that remain. This one, and this one. And then, yes, so this is gone because D is equal to 0. This is gone because the centroid is at the origin. So clear this mess. So we differentiate with respect to phi and setting the derivative to 0. And you can see that, well, you can have closed formula for the tangent of, well, to phi. Yes, if you go to the complex numbers, to the complex plane, then you can actually see that phi is the angle of the square root of this sum x plus I times y squared. Here I is the imaginary unit. I squared is equal to -1. Anyway, so you have this closed formula solution for the angle at which the optimal line passes, the angle for its slope, and you know that it should pass through the centroid of the set of points, just as in the regression line doesn't have to pass through, but again, the centroid is kind of central to this formula. So yes, you know the answer, how the optimal line should go. So that was about minimizing the sum of squared distances to the line. Now, there are other measures that we can consider for finding a line that fits well a set of points. So yeah, you can have the line that minimizes the sum of distances, and we can consider the line that minimizes the maximum distance to the point set. So let me start from this second objective function, minimizing the maximum distance to your point. So you have lots and lots of points, and you want to find a line that minimizes the maximum distance to it. So maybe this is the maximum distance out of all the blue points. And one observation is that maybe there shouldn't be only one blue point that delivers the maximum, that maximizes the distance. Why? Because if there is only one, we can shift the line. So let me go to the next page in the Jamboard.
So I'm resuming the recording and repeating that right now there is only one point in the data set that delivers the maximum. It's this point. And I can decrease the distance to that point by, well, yeah, moving the line in this direction, because then, well, this distance will decrease. And I can do that until, so if I start moving my line, then this whole slab, these 3 lines, this slab, it will move over here, and I can do it until I'm hitting another point on the other side of this slab. So if I were to redraw, I'm not trying to do it exactly in the good, in the same way, at the same points as before, but what I want to say is that, yes, my optimal line should be kind of locked by 2 points, right? So if I'm looking at this slab, then my line will be exactly in the middle of this slab, and I should have 2 points, 2 original points on each side of this slab. Then I will be, well, hopefully in the optimal. So essentially, what I'm trying to find is I'm trying to find the minimum width of the point set. So I have my blue point set, and if I look at any direction, maybe direction like this, then what is the width of the minimum slab, which contains, fully contains all my points, and the slab is perpendicular to this direction? Well, here it is. Maybe I take another direction. I don't know, maybe I take direction like this, and I'm trying to find the minimum width slab perpendicular to this direction. I guess it would be something like this, that contains all my points, all the blue points, right? So as I'm rotating the direction, I'm saying if my slab is going to be perpendicular, or if my line is going to be perpendicular to this direction, then I'm taking a line like that, and I'm moving it until it hits the point. And I'm taking another line at infinity, again in this direction, and I'm moving it until it hits my point set. And this will be the width of my point set in this direction. And what I really want to find is the direction in which the width of the point set is as small as possible. So maybe in this particular case, maybe this is the answer. But the point is that the slab should contain 2 original points on the boundary of the minimum width slab. And in general, the way to find the line that minimizes the maximum distance to the points is to find the minimum width slab that contains your point set, or in other words, find the width of the point set. And I'm not going to go into the algorithms of how you can do that. If you want, you can read about that, but this is the general idea. So if you want to minimize the maximum, sorry, I'm saying here min max, what I really meant is min max. If I want to minimize the maximum, I'll make the correction, hopefully. Right, so if I want to minimize the maximum, I have to be locked from 2 sides. So I have to find the width of the point set. Okay, one last measure that of goodness of fit of a line is, well, minimizing the sum of the distances. So here we're minimizing the sum of squares. If we minimize the sum, then, well, on one hand, things are a bit more complicated than here, because you don't have, you know, a single solution which would, you know, just take your points and put them in. But on the other hand, you have a simpler algorithm for finding the line that minimizes the sum of distances. So again, I'll draw on the Jamboard and go to the next page 7 for that. So what you have here is again a point cloud, and you want to find the line that minimizes the sum of distances. And how would you do that? Well, one thing you can do is you can write the formula for the sum of distances. It will be the formula like this, except that you will not have the square, right? So you will have the summation of xi cosine phi plus yi sine phi plus d. But of course, depending on which side of the line you are, on this or on this, you will have to take this term with plus over the minus. So if you are on one side, then this gives you the distance. If you're on the other side, then minus this gives you the distance. Or in other words, as you move this line parallel to itself, back and forth, which is essentially changing d, if you starting getting closer to some of the points and getting farther from some other points. Like if you move in this direction, then all these points, they become closer to the line. So you are decreasing the distance. And again, if you move in this direction, then all these points are getting farther away from the line. You're increasing the distance. And let me ask you a question. Maybe let me draw an example. So here I have, I don't know, maybe 4 points over here, maybe 3 points over here. And I'm claiming that this is the line that minimizes the sum of distances. Now, but maybe I'll do more points, so I will have 1, 2, 3, 4, 5, 6, 7 points on one side and 5 points on the other side. Okay, so I'm looking now at this example. Can this line be the optimal line, the line that minimizes this, the line that minimizes the sum of distances to my given points? And again, I'm encouraging you to give answers either in the chat or by speaking up, and I will pause. So if you have different number of points on the different sides of the line, then you will want to move the line into the direction where you have more points, because this way you are decreasing more distances. And even if you have the same number of points, you know, like 6 points here, 6 points here, it wouldn't hurt to move the line in either of the directions. And so what we have just proved is that the optimal line will necessarily pass through one of the points. So I will try to draw a last picture on this page. If necessary, I will move to a different page. So we know that our line necessarily is passing through one of the points. Okay, well, what I drew here is not necessarily the optimal line, but it should be a line like this, or maybe a line like this, maybe a line like this, and so on. So you can try the lines going through all the points. And then the question is only, what is the right rotation angle for the line? And I will not write the formulas for you, but you can write the formula. Well, essentially the formula is right here. You have the sum of square distances. Well, you would have to remove the squares, so really take formula like this. And you can see that if you rotate the line, that is, if you change the angle of the line, then you will necessarily be at the minimum at one of the extreme points when the line passes through 2 points. Okay. So this gives you the algorithm. if you want to find the line that minimizes the sum of the distances to given points, then you should just try all the lines that going through two of your points. So you take every pair of your points, draw a line through them, and among those lines, you choose the best. There's no closed form solution, nothing as beautiful as this one, but still, there is an algorithm. Okay, so we have 3 minutes remaining. Of course, I will not start a new topic.